Modern Age MCQs, Physics Class 2nd Year, Unit 13, Electromagnetism, Part 3. From a beam of electrons, an experimenter separates electrons of speed 10 power 6 meter per second by using velocity selector. He applied electric field and magnetic field in the ratio. Option A, 10 power 12 to 10 power 11. Option B, 10 power 12 to 10 power 9. Option C, 10 power 12 to 10 power 6. Option D, 10 power 12 to 10 power 3. The key is 10 power 12 to 10 power 6. Therefore, the correct option is C. Reason: the working of a velocity selector is based on cross electric and magnetic fields. If the net force provided by two fields is zero, then the charged particles move along a straight line with speed v is equal to E divided by B, where E is the electric field and B is the magnetic field. Therefore, for the speed 10 power 6 meter per second, we have E divided by B equal to V divided by 1, which is equal to 10 power 6 divided by 1, which can be written as 10 power 12 divided by 10 power 6. Hence, the ratio E to B is 10 power 12 to 10 power 6. A metallic loop is placed in a magnetic field B. The magnetic flux through the loop is minimum if the angle between B and area A of the loop is option A 0 degree, option B 45 degree, option C 90 degree, option D 135 degree. The key is 90 degree. Therefore, the correct option is C. Reason: the magnetic flux through the loop is phi is equal to B dot A, which is equal to B A cos theta. The flux is minimum, maybe 0. Therefore, cos theta is equal to 0 or theta is equal to 90 degree. Hence, the angle between B and area A of the loop is 90 degree. A current I through a conductor produces magnetic flux density at a distance r given by option A mu naught I divided by pi r, option B mu naught I divided by 2 pi r, option C mu naught I divided by 3 pi r, option D mu naught I divided by 4 pi r. The key is mu naught I divided by 2 pi r. Therefore, the correct option is B. Reason: by Ampere's law, the magnetic flux density due to a current I in a conductor at a distance r is B is equal to mu naught I divided by 2 pi r. Hence, the magnetic flux density is mu naught I divided by 2 pi r. A current of 2 ampere through a conductor produces magnetic flux density at 32 centimeter. Option A 1 mu naught Weber per square meter, B 2 mu naught Weber per meter square, C 3 mu naught Weber per square meter, B 4 mu naught Weber per square meter. The key is 1 mu naught Weber per square meter. Therefore, the correct option is A. Reason: by Ampere's law, the magnetic flux density is B is equal to mu naught I divided by 2 pi r. Therefore, B is equal to mu naught into 2 divided by 2 pi into 0.32, because 32 centimeter is equal to 0.32 meter. Or B is equal to 1 mu naught Weber per square meter. Hence, the magnetic flux density is 1 mu naught Weber per square meter. Note, 1 by pi is equal to 0.318. Therefore, pi into 0.32 is equal to 1. An Amperian path is option A is circular path, option B is square path, option C an enclosed path, option D an elliptic path. The key is any closed path. Therefore, the correct option is C. Reason. The mathematical statement of Ampere's law is sigma B vector dot delta L vector, which is equal to mu naught into I, where I is the current. Therefore, sigma B vector dot delta L vector is equal to B vector dot delta L1 plus B vector dot delta L vector 2 plus and so on. And in this equation, sigma delta L vector is equal to delta L1 plus delta L2 and so on is the length of any closed path around a current. Hence, an Amperian path is any closed path enclosing the current I. The magnetic induction in a solenoid can be changed by changing number 1 current, number 2 turns, number 3 core. The options are A 1 and 2, option B 2 and 3, option C 3 and 1, option D 1, 2 and 3. Therefore, the key is 1, 2 and 3. The correct option is D. Reason. The magnetic induction inside a current carrying solenoid is B equal to mu and I. In this relation, mu is the permeability of core, N is the number of turns per unit length, and I is the current in the solenoid. Therefore, the magnetic induction B in a solenoid can be changed by changing number 1 current, number 2 turns, and number 3 core. Hence, the option D is correct. A current carrying rectangular coil of galvanometer is placed in a magnetic field produced by cylindrical pole faces of a magnet. The angle between face of coil and field at any instant is option A 0 degree, option B 45 degree, option C 90 degree, option D 135 degree. The key is 0 degree. Therefore, the correct option is A. Reason. The cylindrical pole faces of magnet generate radial field. Therefore, the angle between face of coil and field at any instant is theta is equal to 0 degree. Hence, the angle between face of coil and magnetic field is 0 degree. The torque acting on a current carrying coil of galvanometer in a radial field is option A N B A, where N is the number of turns, B is the magnetic induction, A is the area of cross section of the coil. B N I A. In this equation, I is the current. C N B I. D N B I A. The key is N B I A. Therefore, the correct option is D. Reason. The torque acting on a current carrying coil in a magnetic field B is torque tau is equal to N B I A cos theta. When field is radial, theta is equal to 0 and cos theta is equal to cos 0, which is equal to 1. Therefore, the torque acting at the coil is equal to NBIA. Hence, the torque acting on a current carrying coil is NBIA. When a circuit is disconnected from galvanometer, then the torque acting on the coil is Option A, torque tau is equal to 0. Option B, torque tau greater than 0. Option C, torque tau less than 0. Option D, torque tau less than or equal to 0. The key is torque tau is equal to 0. Therefore, the correct option is A. Reason. The torque acting on the coil is tau equal to B-I-N-A, where B is the magnetic induction, I is the current, N is the number of turns, A is the area of the coil. When the circuit is disconnected, current I is equal to 0. Therefore, the torque tau is equal to B into 0 and A or torque tau is equal to 0. Hence, the torque acting on the coil is tau is equal to 0. The expression torque tau is equal to C theta is for a galvanometer. The constant C is called restoring torque. The SI unit of C is option A, kilogram meter per second. Option B, kilogram meter square per second. Option C, kilogram meter square second square. Option D, kilogram meter square per seconds. The key is kilogram meter square per second. Therefore, the correct option is B. Reason. The SI unit of restoring torque C is same as the torque because theta has no dimensions. The unit of torque is kilogram meter square per second. Hence, the SI unit of C is kilogram meter square per second.